Tonight we're diving into the soothing development of Islamic Golden Age mathematics and scholarly methodology. Forget everything Hollywood told you. This is the real story. And trust me, you probably wouldn't last a day. So before you get too comfortable, hit that like button if you enjoy this kind of deep dive, and let me know in the comments where you're watching from. Now, dim the lights, maybe grab a snack, and let's jump in. You wake up in Baghdad, year 832. The smell hits you first, a mixture of burning oil lamps, fresh papyrus, and something that might be last night's lamb stew wafting from the courtyard below. Your head pounds. Not from wine, mind you, because you're in the heart of the Abbasid Caliphate and alcohol is strictly off the menu. No, your headache comes from staying up until dawn, calculating the square root of negative numbers. Welcome to the House of Wisdom, where sleep deprivation is a badge of honor, and your biggest flex is solving equations that won't be rediscovered in Europe for another 400 years. You stumble out of your small chamber, nearly tripping over a stack of manuscripts that cost more than most people's houses. The morning call to prayer echoes across the city, but you're already late for your meeting with the chief librarian. As you rush through the marble corridors, your sandals slapping against the cool stone, you pass scholars from Persia, India, Greece, and even China. They're all here for the same reason you are. The Caliph pays in gold for anyone who can translate, preserve, or expand upon the world's knowledge. And when I say gold, I mean literal gold coins that would make a modern tech startup signing bonus look like pocket change. The thing is, you're not just here to copy old Greek texts like some medieval photocopier. No, you're part of something bigger, something that would make Silicon Valley jealous. This is the world's first think tank, research university, and Google headquarters all rolled into one. Except instead of coding in Python, you're working with Arabic numerals that you just imported from India. Yeah, those numbers you use every day. The ones on your phone screen right now, they didn't come from Rome or Greece. They came from scholars like you, sweating in the Baghdad heat, arguing about whether zero is a real number, or just a philosophical concept. Let me paint you a picture of your workplace. The House of Wisdom isn't some dusty library with cranky librarians shushing everyone. It's a massive complex with observatories, translation rooms, debate halls, and even a hospital where doctors are performing cataract surgery while European healers are still prescribing leeches for everything. The walls are covered with geometric patterns, so complex they'd make MC Escher weep. The courtyard fountains don't just provide cool air, they're precisely calculated to create acoustic effects that help with concentration. Even the architecture is showing off. Your colleagues aren't just mathematicians either. There's Al-Khwarizmi down the hall, literally inventing algebra while you were sleeping. His name is where we get the word algorithm from, by the way. Drop that at your next dinner party and watch people's faces. Then there's Al-Kindi, who's somehow juggling cryptography, philosophy, medicine, and music theory, like some kind of 9th century Renaissance man before the Renaissance was even a thing. These guys make modern multitaskers look like underachievers. The librarian finally tracks you down, and he's not happy. Apparently you were supposed to present your findings on Indian decimal notation to a visiting delegation from Cordoba. You grab your notes, written on paper, actual paper, not parchment, because the Muslims learned papermaking from Chinese prisoners of war and turned it into an art form. Europeans are still scraping sheepskin while you're mass-producing books like it's nothing. As you enter the presentation hall, you notice the delegation looking skeptical. They've traveled for months to get here, crossing deserts and dodging bandits, all to see if Baghdad's reputation is deserved. You clear your throat and begin explaining how the Indian number system works. You write a simple equation on the board, something like 534 plus 289, In Roman numerals, this would be dxx fourth plus cclxxxxx, and good luck doing that in your head. But with your Hindu Arabic numerals, it's child's play. You can see their eyes widen as you demonstrate multiplication and division with an ease that would seem like magic to anyone still using an abacus. But here's where it gets interesting. You're not just showing them party tricks. You're explaining how these numbers allow for something revolutionary, the ability to express infinite concepts in finite terms. You can write any number, no matter how large, with just 10 symbols. You can express parts of wholes with fractions that actually make sense. You can even start playing with that weird concept from India called sunya, or emptiness, which you Arabs calls ifar. Europeans will later mangle this into zero, but right now, in this moment, you're blowing minds with the idea that nothing can be something. The delegation starts firing questions at you. How do you handle calculations for inheritance law when the fractions get complicated? Easy, you've developed something called algebra specifically for that. What about calculating prayer times for different latitudes? You pull out an astrolabe, a device so sophisticated that it won't be improved upon for another 5 centuries. Someone asks about the phases of the moon. You casually mention that your colleague down the hall just figured out that the moon's surface has mountains, about 700 years before Galileo will claim credit for the same discovery. But the real kicker comes when someone challenges you to solve a practical problem. A merchant needs to know how much grain he can fit in a cylindrical silo. In Europe they'd estimate and pray. Here you whip out geometric formulas that would make Pythagoras jealous. You're calculating volumes and areas with a precision that won't be matched in the West until Newton shows up. And you do it all while explaining your methodology, because in the House of Wisdom, showing your work is just as important as getting the right answer. The thing that really sets Islamic mathematics apart isn't just the calculations, it's the systematic approach. You don't just solve problems, you create reproducible methods. You write everything down, you peer review each other's work, and you build on previous discoveries. It's the scientific method, centuries before anyone calls it that. While European monks are copying manuscripts with errors that compound over generations, you're developing standardized notation and rigorous proofs. You're creating a language of mathematics that will become universal. After your presentation, you head to the afternoon symposium. This is where things get really wild. Picture a TED Talk, but everyone in the audience is a genius. And heckling is not just allowed, but encouraged. Today's topic is whether mathematics exists independently of human thought, or if it's just something we made up. Heavy stuff for a Tuesday afternoon. But this is your normal. The debate gets heated. One scholar argues that numbers are divine, written into the fabric of reality by Allah. Another counters that mathematics is just a human tool, no more real than poetry or music. You jump in with a third option. Maybe mathematics is the language God uses to speak to us. The room erupts. Someone throws a cushion. Academic discourse in the Islamic Golden Age is a full contact sport. But here's what's beautiful about this chaos. It's productive. By the end of the session, you've all agreed to test your theories through observation and calculation. One group will study the movement of planets to see if mathematical laws govern the heavens. Another will examine the patterns in plant growth. A third will analyze the harmonics of musical instruments. It's empirical research, hypothesis testing, and peer review, all happening while Europe is still arguing about how many angels can dance on the head of a pin. You take a break in the courtyard, where the afternoon heat makes the air shimmer. A servant brings you sherbet, not the frozen kind you're thinking of, but a cool drink made with fruit syrups and snow brought down from the mountains. Yeah, they have refrigeration logistics figured out in the 9th century. As you sip your drink, you overhear two scholars arguing about infinity. not in abstract terms, but in practical ones. If you keep dividing a number by 2, do you ever reach 0? Can you have different sizes of infinity? These questions won't be formally answered in Europe until Cantor goes mad trying to solve them 1,000 years from now. The conversation shifts to optics, and suddenly everyone's pulling out crystals and mirrors. Ibn al-Haytham joins your group. He's the guy who figured out how vision actually works. While Europeans still think the eye shoots out rays to see things, like some kind of biological laser, he's proven that light enters the eye. He's basically invented the scientific method while studying how we see. He sets up an impromptu experiment right there in the courtyard, using a dark chamber with a small hole to project an image. You're watching the principle behind every camera that will ever be invented, demonstrated with nothing but a box and sunlight. As the sun sets, painting Baghdad's skyline in shades of gold and crimson, you realize something profound. You're not just preserving ancient knowledge, you're creating new knowledge at a rate the world has never seen before. Every day someone in this building is making a discovery that would win a Nobel Prize in the modern era. But here it's just Tuesday. Tomorrow you'll probably invent 3 new mathematical concepts before lunch. Comment below if you think you could handle this kind of intellectual pressure, because honestly, most of us would tap out after the first theoretical physics debate. The next morning arrives too soon, and with it comes your worst nightmare. You've been assigned to the translation department. Now, before you groan, let me explain why this is actually where the real magic happens. You're not just converting words from Greek to Arabic. You're taking concepts that don't even exist in Arabic yet, and creating an entirely new vocabulary. Imagine trying to explain cryptocurrency to Shakespeare. That's your job, except with ancient Greek mathematics. You sit down with a manuscript of Euclid's Elements that looks like it's been through a war, which it probably has. This particular copy was rescued from Constantinople, smuggled through Syria, nearly lost in a sandstorm, and finally made it to Baghdad, with half its pages water damaged. Your job is to not only translate it, but to fill in the gaps using mathematical logic. It's like doing a jigsaw puzzle, where half the pieces are missing, and you have to carve new ones that fit perfectly. Your translation partner is a Nestorian Christian named Hunayn ibn Ishaq, and this guy is a linguistic superhero. He speaks Arabic, Syriac, Greek, and Persian fluently. He doesn't just translate, he improves. When he finds an error in the Greek text, he fixes it. When he encounters a concept that needs clarification, he adds commentary. European scholars will later think these additions are part of the original text, and spend centuries trying to figure out why ancient Greeks knew so much about algebra. The process is mind-numbing and exhilarating at the same time. You spend 3 hours arguing about how to translate a single Greek term for a type of geometric proof. The Greek word has no Arabic equivalent, so you have to invent one. You try 6 different options, each one slightly changing the meaning. Finally, Hunayn suggests using a metaphor from architecture, the way an arch distributes weight. Suddenly, the concept clicks. You've just created a new way of thinking about mathematical proofs that will influence how every Arabic-speaking mathematician understands geometry for the next millennium. But translation isn't just about language. It's about cultural transmission. The Greeks had a different way of thinking about numbers than the Indians, who thought differently from the Chinese. Your job is to take all these different traditions and synthesize them into something new. You're creating a mathematical lingua franca that will spread from Spain to India. When European scholars finally discover your translations 400 years later, they'll think they're reading pure Greek texts. They have no idea they're actually reading Greek filtered through Arabic, enhanced with Indian numerals and seasoned with Persian commentary. The translation room is a Tower of Babel in reverse. Instead of languages splitting apart, They're coming together. You've got a Jewish scholar from Andalusia working on Hebrew astronomical texts, a Zoroastrian from Persia translating ancient Babylonian star charts, and a Buddhist from Central Asia explaining Indian concepts of zero and infinity. The religious diversity would make a modern HR department nervous, but here everyone's united by a common goal, the pursuit of knowledge. The Caliph doesn't care if you pray to Allah, Yahweh, Ahura Mazda, or Buddha, as long as you can translate, calculate, or discover. Lunch break means heading to the marketplace, and this is where you see how mathematics affects real life in the Islamic Golden Age. The market inspectors, called mutasibs, are using algebra to check if merchants are cheating on weights and measures. They carry standardized scales and use geometric principles to verify volumes. One merchant claims his spherical containers hold exactly 100 units of grain. The mutasib pulls out a measuring rope and starts calculating. The merchant is off by 3 units, busted by geometry. You watch a money changer converting Byzantine gold to Abbasid dinars. He's not using some simple exchange rate. He's calculating the pure gold content of each coin, adjusting for wear and debasement, and factoring in transportation costs and risk. This guy is doing forex trading with mathematical precision that won't be matched on Wall Street until computers come along. He shows you his ledger, and it's full of algebraic equations. The Islamic prohibition on charging interest has led to incredibly creative mathematical workarounds that are basically derivatives and futures contracts, just with different names. A carpet seller catches your eye, not because of his wares, but because of the geometric patterns. These aren't random designs. They're mathematical tessellations that repeat infinitely without gaps or overlaps. The seller, noticing your interest, starts explaining the mathematics behind his patterns. He's not a scholar, just a craftsman, but he understands geometric principles that most European mathematicians haven't even discovered yet. He shows you how rotating a single shape by specific angles creates patterns of mind-bending complexity. His carpets are basically mathematical proofs you can walk on. You stop by a food stall for some lamb kebab, and even here, mathematics intrudes. The cook is using proportions passed down through generations to mix his spices. But these aren't just grandma's recipes. They're based on the mathematical theory of proportions developed by Al-Khwarizmi, who discovered that pleasure responses follow mathematical ratios. The perfect blend of cardamom to cinnamon to black pepper isn't just tradition, it's mathematically optimized for maximum flavor impact. The Islamic Golden Age has literally calculated the formula for deliciousness. On your way back, you pass by a construction site where they're building a new mosque. The architects aren't just artists, they're mathematical engineers. They're using advanced geometry to calculate load-bearing arches that seem to defy gravity. The famous mutanars, those honeycomb-like decorations that cascade from domes, aren't just pretty, they're three-dimensional geometric puzzles that distribute weight while creating acoustic effects. The head architect shows you his plans, and they look like something from a computer-aided design program, except it's all hand-drawn using compass and straight edge. The real kicker is when you realize that all of this practical mathematics feeds back into theoretical work. The market inspector's problems become algebra exercises. The architect's challenges lead to new geometric theorems. The astronomical calculations for prayer times drive innovations in trigonometry. It's a feedback loop between practical needs and theoretical advancement that won't be replicated until the Industrial Revolution. And it's all happening right here, right now, in the dusty streets of 9th century Baghdad. Back at the House of Wisdom, the afternoon is devoted to your real passion, trying to square the circle. This impossible problem has been driving mathematicians crazy since ancient Greece, and you're convinced you're close to cracking it. You're not, of course. It won't be proven impossible until the 19th century, but the attempts to solve it are pushing mathematics forward in ways you can't even imagine. You're working with a compass and straight, the only tools allowed by classical geometry. But here's where Islamic mathematicians are cheating in the best way possible. You're also using algebra. While Greek geometers were limited to what they could physically construct, you're using algebraic equations to explore geometric relationships. You can prove things exist even if you can't draw them. It's like having X-ray vision for mathematics. Your colleague, a young prodigy from Samarkand, rushes in with excitement. He's been working on cubic equations, the ones where x is raised to the power of 3. The Greeks couldn't solve these geometrically, and neither can you. But by combining Indian numerical methods with Greek geometry and your own algebraic innovations, he's found a way to approximate solutions. He's basically inventing numerical analysis 800 years early. His methods won't be rediscovered in Europe until Cardano claims credit for them in the Renaissance. The conversation turns to trigonometry, and this is where Islamic mathematics really shines. You're not just using sines and cosines, you've got tangents, cotangents, secants, and cosecants. You've got trigonometric tables calculated to 15 decimal places. Why? Because you need them for astronomy, and astronomy is serious business when you need to know exactly which direction Mecca is from any point in the empire. Prayer times, religious festivals, navigation, they all depend on trigonometric calculations that would make a modern high school student cry. But here's the mind-blowing part. You're also developing spherical trigonometry. Flat Earth, please. You're calculating distances on a sphere, figuring out great circle routes, and determining the Earth's circumference with stunning accuracy. Al-Biruni, working in Central Asia, will soon calculate the Earth's radius using nothing but trigonometry and a mountain. His result will be off by only 16 kilometers. NASA would be impressed. As evening approaches, you attend a lecture on the nature of parallel lines. This might sound boring, but it's actually revolutionary. The speaker is questioning Euclid's parallel postulate, the idea that parallel lines never meet. What if they do meet, somewhere at infinity? What if space itself is curved? These ideas won't be fully developed until Lobachevsky and Riemann create non-Euclidean geometry nearly 1,000 years later, but the seeds are being planted right here, in this room, by scholars who dare to question assumptions that Greeks considered sacred. The debate gets philosophical fast. If parallel lines can meet, what does that mean for the nature of reality? Is the universe finite or infinite? Can something be logically true but physically impossible? The discussion continues long into the night, fueled by strong coffee, yes coffee, which the Arabs are importing from Ethiopia and turning into an intellectual performance enhancer. While Europeans are falling asleep in their ale, you're wide awake, arguing about the fundamental structure of space itself. Drop a comment if you think coffee-fueled mathematical debates sound like your ideal Friday night, because honestly this is peak nerd culture, and I'm here for it. Day 3 starts with a bang. Literally. Someone in the chemistry department, which they call the alchemy department, because branding wasn't their strong suit, just blew up part of their lab trying to transmute lead into gold. The explosion rattles your windows and sends scholars running to see what happened. The alchemist emerges from the smoke, eyebrows singed, clothes covered in some mysterious green powder, proudly declaring he's discovered a new way to make glass. Task failed successfully. This is the thing about Islamic Golden Age science. Failure is just data. While the alchemist didn't make gold, He did stumble upon a chemical reaction that produces a harder, clearer glass than anything currently available. Within hours, the astronomers are commissioning new lenses for their telescopes. The medical department wants magnifying glasses for surgery. Everyone sees opportunity where others might see disaster. The scientific method isn't just about proving hypotheses, it's about learning from every experiment, even the ones that blow up in your face. You're called to help calculate the chemical proportions for the new glass formula. This is where mathematics meets chemistry in ways that won't happen in Europe for centuries. You're using algebra to balance chemical equations before anyone even knows what molecules are. The alchemists have noticed that reactions follow specific proportions. 2 parts of this substance always combine with 3 parts of that one. They don't know why, but they can calculate it. You're basically doing Stoic geometry without atomic theory, which is like performing surgery blindfolded, but somehow still succeeding. The head alchemist, Jabir ibn Hayyan, shows you his laboratory notebooks. This guy is the father of chemistry, though he doesn't know it yet. His notes are filled with measurements, observations, and mathematical relationships. He's classified substances by their properties, metals, stones, spirits, salts, and discovered that each category follows different mathematical rules when combining. He's even developed a theory that all metals are made of 2 principles, sulfur and mercury, in different proportions. It's wrong, but it's systematically wrong, in a way that advances science. You help him design an experiment to test his latest theory about crystallization. He believes crystals grow according to geometric principles, and he's not wrong. You set up a series of solutions with different concentrations, calculated precisely using algebraic formulas. Over the coming weeks, you'll observe how crystals form, measuring angles, counting faces, documenting patterns. You're discovering the mathematical laws of crystallography 900 years before X-ray diffraction confirms them. The real innovation here isn't just the experiments, it's the documentation. Every measurement is recorded, every observation is dated and signed. Multiple scholars witness each experiment. Failed experiments are documented just as carefully as successful ones. You're creating the world's first peer-reviewed scientific journals, except they're handwritten on paper you made yourself. When historians later wonder how Islamic science advanced so quickly, this is why. You're not just doing science, you're creating a scientific infrastructure that preserves and transmits knowledge across generations and continents. After cleaning the green powder off your clothes, which you suspect might be toxic, but haven't invented workplace safety yet, you head to the medical wing. This is where mathematics gets literally life-saving. The doctors here aren't just following ancient Greek texts, they're conducting clinical trials with statistical analysis. They're tracking patient outcomes, calculating dosages based on body weight, and using probability to predict disease outbreaks. The chief physician, Al-Khwarizmi, is examining a patient with a fever, but he's not just feeling the forehead and prescribing bloodletting like his European counterparts. He's taking detailed notes, temperature changes over time, pulse rate, breathing patterns. He shows you charts where he's tracked similar cases, looking for patterns. He's discovered that certain fever patterns indicate specific diseases. He's basically invented diagnostic algorithms using nothing but observation and mathematics. You watch him prepare medicine, and it's like watching a mathematical equation come to life. He calculates doses based on the patient's weight, age, and severity of symptoms. He adjusts for the concentration of active ingredients, which varies depending on where the herbs were grown and when they were harvested. He even factors in the time of day the medicine will be taken, having noticed that the body processes substances differently at different times. This is personalized medicine with 9th century technology. The surgical department is even more impressive. They're performing cataract surgery using instruments so precise they could be in a modern operating room. The angles of the cutting tools are calculated using geometry. The surgeons practice on eyes from sheep, measuring exactly how much pressure to apply, at what angle for how long. They've turned surgery into applied mathematics. Success rates are tracked, techniques are standardized, and innovations are shared across the entire Islamic world. But here's what really blows your mind. They're using statistics to track disease outbreaks. They've noticed that certain diseases follow mathematical patterns. Outbreaks peak at predictable intervals. Diseases spread along trade routes at calculable rates. They're doing epidemiology before germ theory exists. One physician shows you a map where he's tracked the spread of a recent outbreak, using mathematics to predict which cities will be affected next. His predictions are eerily accurate, all based on mathematical models of human movement and interaction. The pharmacy attached to the hospital is basically a mathematical laboratory. Every compound is standardized, every mixture precisely measured. They've discovered that many medicines follow a dose-response curve. Too little doesn't work, too much is toxic, but there's a mathematical sweet spot in between. They're calculating therapeutic windows and safety margins. The head pharmacist shows you tables of drug interactions, all derived from careful observation and mathematical analysis. Medieval Europe is still using prayer and herbs picked during full moons, while you're calculating molecular ratios without knowing what molecules are. The afternoon brings a special treat. A visiting scholar from India is demonstrating advanced calculation techniques. This guy can multiply huge numbers in his head faster than you can write them down. But he's not just showing off, he's teaching the mathematical principles behind mental calculation. It's like watching a magician reveal his tricks, except the magic is mathematics. He starts with something called the vertically and crosswise method for multiplication. Instead of the laborious process you learned, where you multiply each digit and add up columns, he shows a pattern-based approach that's almost instantaneous. He multiplies 734 by 892 in about 10 seconds, all in his head. The room is silent. Then he explains the method, and suddenly everyone's trying it. Within an hour, scholars who struggled with basic multiplication are solving complex problems mentally. But the real revelation comes when he introduces negative numbers and imaginary numbers. The Islamic scholars have been working with negative numbers for a while. Debt and profit calculations require them. But imaginary numbers, the square root of -1, this breaks brains. How can something that doesn't exist be useful in mathematics? The Indian scholar smiles and shows how these impossible numbers solve real equations. Problems that were unsolvable suddenly have solutions, just not solutions you can point to in the real world. The discussion that follows is intense. Some scholars argue that mathematics should only deal with real things. Others contend that mathematics is pure abstraction anyway, so why not embrace the imaginary? You jump in with a practical application, using imaginary numbers to solve cubic equations. It works, even though nobody really understands why. It's like discovering a cheat code for reality, except the cheat code is written in mathematics that shouldn't exist. The Indian scholar then demonstrates the decimal system for fractions. Instead of writing fractions like 1/3 or 7/11, he writes them as infinite decimals, 0.33 and 0.636363. The precision is intoxicating. You can calculate to any accuracy you want just by adding more decimal places. But then someone asks about 1/3 plus 1/3 plus 1/3. In decimals, that's 0.333 plus 0.333 plus 0.333 which equals 0.99. But shouldn't that equal 1? The room erupts in debate. Does 0.999 equal 1? It's a question that will torment mathematicians for centuries. As the sun sets over Baghdad, painting the Tigris River gold, you realize you've just witnessed something extraordinary. Mathematical concepts that won't reach Europe for hundreds of years are being casually discussed over afternoon tea. The Indian scholar promises to return next month with more advanced concepts, something about infinite series and calculating the value of pi to hundreds of decimal places. Your head spins with possibilities. In medieval Europe, scholars are still arguing about whether zero is heretical. Here you're pushing the boundaries of mathematical imagination so far that reality itself seems negotiable. Let me know in the comments if your brain is melting yet, because we're only on chapter 3 and things are about to get seriously weird. You're jolted awake before dawn by urgent knocking. The Caliph has demanded a solution to a problem that's been plaguing the empire: how to fairly distribute water from the irrigation canals during drought. This isn't theoretical mathematics anymore. Get this wrong and people starve. No pressure. You stumble into an emergency meeting where engineers, mathematicians, and government officials are already deep in heated debate. The problem is deceptively complex. You have one river, dozens of canals, hundreds of farms, each with different water rights based on historical agreements, land size, and crop types. Some farmers paid more taxes and claim they deserve more water. Others have senior rights dating back generations. The traditional method of whoever complains loudest gets the most isn't working anymore. Your team starts by mapping the entire irrigation system. This alone takes 3 days and involves surveying techniques that won't be used in Europe until the Renaissance. You're measuring elevations, calculating flow rates, determining capacity. Every measurement has to be precise, because a small error compounds over hundreds of miles of canals. You're using trigonometry to measure distances across rivers, geometry to calculate water volumes, and algebra to solve for unknown flow rates. But the real challenge is the optimization problem. You need to maximize agricultural output while minimizing conflict. It's not just about distributing water equally. Different crops need different amounts at different times. Date palms can survive with less water than wheat. Rice fields need flooding, while grapevines need just enough but not too much. You're essentially solving a massive system of equations with dozens of variables and constraints. Modern computers would struggle with this. You have an abacus and determination. The breakthrough comes when someone suggests using game theory, though they don't call it that. Instead of imposing a solution from above, create a mathematical system where farmers can trade water rights. If someone needs extra water this week, they can buy it from someone who needs less, with prices determined by supply and demand. But to prevent hoarding and speculation, you add mathematical constraints. No one can buy more than twice their allocation. Prices are capped using a formula based on average rainfall over the past decade. You spend days working out the mathematical framework. Exchange rates between different time periods, water today versus water next week, penalty functions for overuse, bonus allocations for farmers who improve efficiency. It's like designing a cryptocurrency economy, except instead of digital coins, you're trading water rights, and instead of blockchain, you have very serious men with very sharp swords ensuring compliance. The system you've designed is so complex that you need to create a new type of mathematics to explain it to the administrators. You call it administrative algebra mathematics, specifically designed for bureaucracy. You create standardized forms with built-in calculations. Water inspectors just need to fill in measurements, and the mathematics automatically determines allocations. It's the world's first mathematical bureaucracy, and it's beautiful in its efficiency. To test the system, you run simulations using historical data. What would have happened during the drought of 798 if this system had been in place? You calculate that agricultural output would have been 20% higher, and conflicts would have been reduced by half. The officials are impressed but skeptical. How can mathematics prevent people from fighting over water? You demonstrate with a wargame simulation. Different teams represent different regions. They make decisions about water usage based on your mathematical rules. At first, everyone tries to game the system, hoarding water or making suboptimal trades. But as the simulation continues, patterns emerge. Cooperation leads to better outcomes for everyone. The mathematics naturally incentivizes collaboration. It's like watching an invisible hand guide people toward mutual benefit, except the invisible hand is made of equations. The Caliph's advisors want to know about enforcement. How do you prevent cheating? This is where cryptography comes in. Each water allocation is encoded with a mathematical signature that can be verified but not forged. You're basically inventing digital signatures using modular arithmetic. Water inspectors can verify authenticity using simple calculations, but creating a fake allocation would require solving mathematical problems that would take years. The real test comes when you implement the system in a small district outside Baghdad. The first week is chaos. Farmers don't trust the mathematics. They're used to negotiating, bribing, and fighting for water. But slowly they start to see the patterns. The farmer who conserved water last week has extra to sell this week at a premium. The one who wasted water is now paying triple for emergency supplies. The mathematics is teaching them resource management through their purses. Within a month, the test district is outperforming neighboring areas by 30%. Crop yields are up, conflicts are down, and even the tax collectors are happy because the mathematical transparency makes it harder to hide income. The Caliph orders the system rolled out across the empire. You've just revolutionized water management using mathematics, creating a system so effective that variations of it will still be used in modern irrigation systems. Not bad for someone who woke up with a headache 4 days ago. Your success with the water distribution system has made you famous, which in 9th century Baghdad means more work, not vacation time. Now the military wants your help. They're planning a campaign and need to optimize supply lines. The general spreads out a map that covers the entire floor of the meeting room. It shows the route from Baghdad to Damascus, with every town, river, mountain pass, and potential bandit hideout marked. The problem is logistics. An army of 10,000 men needs food, water, weapons, replacement horses, medical supplies, and 100 other things. Too many supplies and you move too slowly. Too few and you starve. Supply caravans are vulnerable to attack, so you need guards, but guards also need supplies. It's a recursive nightmare that makes your head spin. You start with basic calculations. A soldier needs about 3 pounds of food per day. A horse needs 20 pounds of fodder. Marching speed decreases with load. You create equations relating army size, supply weight, travel speed, and consumption rate. The mathematics shows something counterintuitive. A smaller, faster army with precisely calculated supplies can be more effective than a large army that has to stop frequently to resupply. But the real innovation comes when you apply network theory, though you call it caravan mathematics. Instead of one massive supply train, you design a network of smaller caravans taking different routes, timed to converge at specific points. If one caravan is attacked, the others continue. You calculate optimal spacing, too close together, and they're all vulnerable to the same attack, too far apart and they can't support each other. The general is skeptical until you show him the battle simulations. Using colored stones on the map, You wargame different scenarios. Traditional supply lines fail catastrophically when cut. Your distributed network degrades gracefully. Lose 30% of your caravans, and you still have 70% of your supplies. The redundancy is mathematically optimized to balance risk and efficiency. You even calculate psychological factors. Armies fight better when they know supplies are secure. You design the supply network to be visible to the troops. They can see caravans arriving from multiple directions, creating an impression of abundance even when supplies are carefully rationed. It's mathematical psychology, using numbers to manipulate morale. The general is so impressed, he offers you a position as military advisor. You politely decline. You've seen what happens to advisors who give bad advice, and it involves significantly more than just losing tenure. Comment below if you think you'd take the job, because honestly, the pay is amazing, but the severance package is literal. It's been a month since you revolutionized water distribution, and now everyone wants a piece of your mathematical magic. Today's client is more unusual. The Guild of Textile Merchants. They're not interested in irrigation or military strategy. They want you to solve the problem of pattern complexity in silk weaving. Specifically, how many different patterns can be created with their existing looms, and is there a mathematical way to generate new patterns that haven't been seen before? You arrive at the textile workshop, and the assault on your senses is immediate. The air is thick with the smell of silk, dyes, and the oil used to keep the looms running smoothly. The rhythmic clacking of hundreds of looms creates a hypnotic percussion that makes thinking difficult. Workers, mostly women, move between the machines with practiced efficiency, their fingers dancing across threads in patterns that look random but definitely aren't. The master weaver shows you their problem. They have design books going back centuries, filled with geometric patterns of incredible complexity, but they've noticed something disturbing. They keep accidentally recreating old patterns. A weaver spends months developing what she thinks is original, only to find it on page 347 of a dusty pattern book from her grandmother's time. They need a mathematical system to catalog patterns and generate truly new ones. You start by analyzing the constraints. Each loom can handle a specific number of threads. Threads can be raised or lowered in combinations. Colors can be changed at specific intervals. It's essentially a binary system. Thread up or down, color A or B, but with multiple layers. You realize you're looking at an early form of computational logic. These weavers are programming patterns using mechanical switches, creating what amounts to textile algorithms. The mathematics gets complex fast. With just 20 threads and 2 colors, there are over 1 million possible patterns for a single row. Multiply that by the hundreds of rows in a typical silk piece, and the numbers become astronomical. But not all patterns are aesthetically pleasing or structurally sound. Some create weak points in the fabric. Others are too chaotic to be beautiful. You need to find the mathematical sweet spot between complexity and harmony. You develop a classification system based on symmetry groups. Patterns that look different might be mathematically identical, just rotated, reflected, or shifted. By identifying these transformations, you can reduce millions of patterns to a few thousand fundamental types. It's like creating a periodic table of textile patterns. Each fundamental pattern can generate dozens of variations through mathematical transformation. The weavers are skeptical until you demonstrate, taking a simple pattern and showing how 12 different original designs in their books are actually the same pattern transformed. The breakthrough comes when you realize that Islamic geometric patterns follow specific mathematical rules. These aren't arbitrary designs. They're visual representations of mathematical relationships. The 8-pointed star that appears everywhere from mosques to textiles, it's based on the regular octagon, and the square root of 2, the intricate interlacing patterns. They follow rules about over-under crossings that can be expressed algebraically. You work with the master weaver to develop a notation system. Each pattern gets a mathematical signature, a string of numbers and symbols that completely describes it. It's like DNA for textiles. Two weavers on opposite sides of the empire can exchange these signatures and recreate identical patterns without ever seeing the original. You've invented a programming language for looms about 1,000 years before Ada Lovelace will be credited with creating the first computer algorithm. But the real excitement comes when you start generating new patterns mathematically. Instead of trial and error at the loom, you can explore pattern space with pen and paper. You discover that certain mathematical sequences, what will later be called Fibonacci numbers, create naturally pleasing patterns. The golden ratio appears everywhere, not because someone planned it, but because it emerges naturally from the mathematics of efficient thread use. The weavers are initially resistant to your mathematical approach. They're artists, not mathematicians. But when you show them how mathematics can predict which patterns will use the least silk while creating the strongest fabric, their eyes light up with golden gleams. Silk is expensive. Saving even 5% per piece means huge profits. Soon they're eagerly learning your notation system, and younger weavers are coming up with mathematical innovations of their own. One clever weaver realizes that your system can be used for quality control. By calculating the mathematical signature of a finished piece and comparing it to the intended pattern, she can identify errors down to the individual thread. What used to take hours of careful inspection now takes minutes of calculation. Defects that would have been missed are caught before the fabric leaves the workshop. The guild is so impressed they commission you to create a master pattern book, not of designs but of mathematical formulas. Each formula can generate hundreds of patterns, and combining formulas creates even more possibilities. You calculate that your system contains more unique patterns than could be woven if every person on Earth did nothing but weave for the entire age of the universe. The weavers are simultaneously thrilled and terrified. Job security through infinite possibility. Your work with the Textile Guild has caught the attention of the architectural community. If you can mathematically generate patterns for fabric, can you do the same for buildings? The chief architect of the new mosque project wants patterns that are not just beautiful, but mathematically perfect, embodying divine proportion in every tile and arch. The challenge is three-dimensional. Textile patterns are flat, but architectural patterns wrap around domes, flow across walls, and create optical illusions that change as you move through space. The architect shows you his current problem, creating a dome where the pattern appears continuous from any viewing angle. He's been trying for months, wasting countless expensive tiles in failed attempts. You approach it as a topology problem, though that word won't be invented for another 1,000 years. The dome is a hemisphere, and you need to map a flat pattern onto a curved surface without distortion. It's impossible. Literally, mathematically impossible. But impossible problems are just opportunities for creative mathematics. If you can't avoid distortion, can you control it? Can you make the distortion part of the design? You develop a system where the pattern gradually transforms as it rises up the dome. At the base, it's one design. At the apex, it's completely different. But the transformation follows mathematical rules so precise that the change appears natural, even inevitable. It's like watching a flower bloom in slow motion, frozen in tile. The mathematics determines not just the pattern, but the rate of change, creating a visual derivative that guides the eye upward toward heaven. The architect wants to know if this can be standardized. Can other builders use your methods? You create what amounts to an architectural pattern language. Start with base units: triangles, squares, hexagons, octagons. Define transformation rules: rotation by specific angles, scaling by precise ratios, reflection across calculated axes. Combine these elements according to mathematical principles, and beauty emerges automatically. But here's where it gets truly mind-bending. You discover that certain combinations create patterns that appear to move. Static tiles arranged according to your formulas create the illusion of rotation, expansion, flowing water. It's not magic, it's mathematics exploiting quirks in human perception. The patterns activate something primal in the brain's visual processing, creating motion from stillness. Medieval Islamic architects are basically creating optical illusions that won't be understood scientifically until neuroscience discovers how vision works. The architect is so excited, he commissions patterns that tell mathematical stories, walls where the pattern represents the expansion of numbers, domes that embody infinite sequences, floors that teach geometry to anyone who walks across them. You've turned architecture into three-dimensional mathematics that people can inhabit. How's that for applied math? The next morning brings disturbing news. Pirates have been attacking merchant ships, using a new strategy that seems to anticipate the merchant's every move. The harbor master suspects they have a spy, but you suspect something else. They've cracked the merchant's navigation patterns. You're called in to investigate, and suddenly you're doing maritime security analysis in the 9th century. The harbor master shows you the attack records, red pins on a map mark where ships were hit. At first it looks random, but you start seeing patterns. The attacks cluster around specific coordinates. You pull out navigation charts and overlay them with the attack sites. The pattern becomes clear. The pirates aren't randomly hunting. They're positioning themselves at mathematical intersection points where multiple trade routes converge. You interview surviving merchants, and a disturbing picture emerges. The pirates seem to know not just where ships will be, but when they appear out of nowhere, strike and vanish before help arrives. It's too precise to be luck. You start analyzing the mathematical patterns in shipping schedules. Merchants, it turns out, are creatures of habit. They leave port at specific times to catch favorable winds. They follow routes optimized for speed, not variety. Their predictability is their vulnerability. The solution requires game theory, though you call it strategic mathematics. If merchants are predictable, make them randomly unpredictable, but controlled randomness, not chaos. You develop a system where each ship's departure time and route are determined by mathematical formula, incorporating random elements. The captain throws dice, consults a table you've created, and gets his instructions. Even he doesn't know his route until the last moment. But pure randomness would be inefficient. Ships might take routes that add weeks to their journey, so you constrain the randomness mathematically. Routes must be within 10% of optimal distance. Departure times must align with tide tables. The randomness is bounded by practical constraints, creating what you call controlled chaos. It's unpredictable enough to confuse pirates, but efficient enough to remain profitable. The merchants are skeptical. They've been navigating the same routes for generations. Why should they trust mathematics over experience? You run a demonstration. Using historical data, you show that if they had used your system, 70% of recent pirate attacks would have missed their targets. The pirates would have been waiting at empty ocean, while ships passed safely miles away. Mathematics as invisibility cloak. Implementing the anti-piracy system reveals a deeper problem. The merchants can follow your randomization tables, but they still need to navigate accurately to reach their randomized destinations. Current navigation methods are imprecise. A small error at the beginning of a voyage compounds over days at sea. Ships aiming for Alexandria sometimes end up in Cyprus. Your random routes are useless if captains can't follow them accurately. You dive into navigation mathematics with an intensity that surprises even you. The astrolabe, that gorgeous brass instrument that looks like steampunk art, is actually an analog computer for solving spherical trigonometry problems. But most navigators use it wrong. They've memorized procedures without understanding the mathematics. It's like using a smartphone by randomly tapping until something works. You develop a navigation manual that teaches the mathematical principles. Start with the basics. The Earth is a sphere, not a flat plane. This means that straight lines on maps aren't actually the shortest routes. Great circle routes save distance but require constant course corrections. You create tables showing optimal heading changes for common voyages. Following your tables, a ship sailing from Basra to Alexandria saves 3 days and considerable supplies. But the real innovation is error correction. Navigation is never perfect. Clouds hide stars, instruments have margins of error, humans make mistakes. Instead of pretending these errors don't exist, you build them into the mathematics. You develop a system of bounded approximation. If navigators know their maximum possible error, they can calculate a zone of uncertainty. As long as they keep their destination within that zone, they'll arrive safely. The mathematical breakthrough comes when you realize that multiple imprecise measurements can combine to create precision. Take a noon sun sight, accurate for latitude but useless for longitude. Combine it with star sights, compass readings, and dead reckoning, each imprecise alone, but mathematically combined, weighted by their individual reliability, they produce a position fix accurate to within a few miles. It's statistical navigation, using probability theory to find your way across featureless ocean. You test the system with a veteran captain who's skeptical of landlubber mathematics. He follows your methods on a voyage to India, maintaining 2 logs, one using traditional navigation, one using your mathematical system. Halfway through the voyage, he's convinced you're leading him astray. Your calculations put him 50 miles from where his experience says he should be. But when land appears exactly where your mathematics predicted, not where tradition suggested, he becomes your biggest advocate. Mathematics has trumped intuition, and the implications ripple through the maritime community. The success of your navigation system leads to an unexpected request. The Caliph's treasure fleet, carrying the annual tribute from Egypt, has gone missing. It's not pirates. No ransom demands, no wreckage. The ships just vanished somewhere in the eastern Mediterranean. The admiral wants you to find them using mathematics. No pressure, just the entire imperial treasury lost at sea. You start with what you know. The fleet left Alexandria 15 days ago. They were last seen passing Cyprus. Weather records show a storm system moving through the area. Ocean currents in that region flow in predictable patterns. It's a massive system of equations with one solution. Where are those ships? You build what amounts to a medieval Monte Carlo simulation. Using dice and probability tables, you model thousands of possible scenarios. What if they were caught in the storm? Where would the wind and currents carry them? What if they avoided the storm, but had to change course? What's the maximum distance they could have traveled? Each scenario produces a probable location. Plot enough scenarios, and patterns emerge. Indward The mathematics points to 3 likely areas. One is a standard refuge, a sheltered bay where damaged ships often take shelter. The second is more concerning, a stretch of coast known for reefs, where currents might have driven storm-damaged vessels. The third is unexpected, an area of open ocean where, if your calculations are correct, the ships might be drifting with broken masts, alive but unable to make way. The admiral is skeptical of searching open ocean based on mathematical speculation, but he's desperate enough to try. He sends fast scouts to all three locations. The sheltered bay is empty. The reef coast shows no wreckage. But in the open ocean, exactly where your calculations predicted, they find the treasure fleet. Masts broken by the storm, but hulls intact drifting in a circular current your mathematics had identified. The rescue is successful, but what really amazes everyone is the precision. You predicted the fleet's location within 2 miles using nothing but mathematics, weather records, and probability. The Caliph is so impressed he establishes a new position, Royal Mathematical Advisor, with a salary that makes other scholars weep with envy. You've just invented search and rescue operations research, using mathematics to find needles in ocean-sized haystacks. The pirates, by the way, are furious. Your randomization system has cut their success rate by 80%. Some have given up piracy entirely, deciding that honest trade is easier than trying to outsmart mathematics. Others have started hiring their own mathematicians, leading to an arms race of algorithmic warfare on the high seas. You've basically started the world's first cyber war, except instead of computers, it's fought with astrolabes and dice. Leave a comment if you think medieval algorithmic piracy sounds like the best video game never made. Your fame as the mathematical miracle worker has spread beyond Baghdad. A messenger arrives from Cordoba, the glittering capital of Islamic Spain. The emir has a problem that requires your unique skills. The city's famous library, second only to Baghdad's House of Wisdom, is in chaos. They have over 400,000 books, and nobody can find anything. The old librarian who had the entire collection memorized just died, taking the organizational system with him to paradise. The journey to Cordoba takes 2 months, giving you plenty of time to think about the problem. How do you organize information so that anyone can find anything? The obvious answer, alphabetical order, doesn't work when you have books in Arabic, Latin, Greek, Hebrew, and a dozen other languages. Subject matter classification, too subjective. One person's astronomy is another's astrology. You need something more fundamental, more mathematical. You arrive in Cordoba to find the library in complete disarray. Scholars are wandering the stacks like lost souls, searching for books they know exist but can't locate. Some have been looking for the same manuscript for weeks. The new librarian is near tears. He shows you the previous system, or what he understands of it. Books were organized by a complex method involving acquisition date, donor name, physical size, and subject matter, all modified by the old librarian's personal opinions about importance. It's like trying to solve an equation where half the variables are subjective and the other half are missing. You start with a radical idea, forget the old system entirely. Instead, create a mathematical classification that transcends language and subject. Every concept you propose can be reduced to numerical relationships. Start with broad categories, assign them prime numbers. Subdivisions get composite numbers based on their parent categories. It's essentially a decimal system for knowledge, where a book's location can be calculated rather than memorized. The librarians are horrified. Reduce the poetry of Ibn Arabi to mere numbers. Classify the Holy Quran with the same system as medical texts. But you demonstrate the beauty of the mathematics. Related subjects naturally cluster together because their numbers share factors. Books on algebra and geometry end up near each other, not because someone decided they should, but because the mathematics of classification mirrors the mathematics of knowledge itself, you develop what amounts to a hash function for books. Title, author, subject, and key concepts get converted to numbers using a standardized algorithm. Combine these numbers using modular arithmetic, and you get a unique identifier that also encodes the book's relationships to other books. It's like DNA for books, a numerical sequence that contains all essential information about the text. The real challenge comes when you start implementing the system. You need to classify 400,000 books, and you have a team of scribes who can barely multiply. The solution is to create mathematical tools so simple that anyone can use them. You design circular slide rules specifically for library classification. Rotate one disk to the subject, another to the author's name, and read off the classification number. It's analog computing for library science, but classification is only half the problem. You also need a way for scholars to find books without knowing their exact classification. You invent what's essentially a medieval search engine, cross-reference tables, where looking up one concept points you to related concepts. Chain these references together, and you can navigate from any idea to any other idea through mathematical relationships. It's like creating hyperlinks out of paper and ink. The system reveals surprises. Books that nobody thought were related turn out to share mathematical signatures. A text on agriculture and a treatise on astronomy have similar numbers because both deal with seasonal cycles. Medical texts cluster near chemical texts, which cluster near cooking manuscripts. The mathematics is revealing hidden connections in human knowledge. Scholars start making discoveries just by browsing mathematically adjacent shelves. You also solve the problem of duplicate texts. Many books are copies of copies, each with small variations. Your mathematical signature system can identify these relationships. Calculate the signature of a new acquisition, and you immediately know if you already have that text or a variation of it. You can even calculate how different two versions are by comparing their numerical signatures. It's version control for medieval manuscripts. The Cordoba Library becomes a marvel of efficiency. Scholars visit from across the known world, not just for the books, but to learn the classification system. Your mathematical method spreads to libraries in Cairo, Damascus, Samarkand. You've created the first international standard for information organization. Books can be referenced by number in letters between scholars, and everyone knows exactly which text is meant. But the real revolution is in how scholars think about knowledge itself. By reducing ideas to numbers, you've made it possible to perform calculations on concepts. Want to find the intersection of Greek philosophy and Islamic law? Calculate it. Looking for texts that bridge medicine and astronomy? There's a formula for that. You've turned the library into a giant calculator where the operations are performed on human knowledge rather than mere numbers. Your success in Cordoba attracts attention from an unexpected source, the secret society of translators. These are the unsung heroes of the Islamic Golden Age, working in basement rooms and monastery cells, converting the world's knowledge from one language to another. They have a proposition that sounds impossible even by your standards. Can mathematics help with translation itself? The problem they present is fascinating. When translating complex philosophical or scientific texts, meaning often gets lost, not because translators don't understand the languages, but because concepts don't map perfectly between cultures. The Greek concept of logos doesn't have an exact Arabic equivalent. Indian mathematical terms describe concepts that don't exist in Latin. Every translation is an approximation, and errors compound when texts are translated through multiple languages. You approach this like a signal processing problem, though that term won't exist for another millennium. Think of the original text as a signal. Translation adds noise. Multiple translations add more noise. Eventually the signal is lost in the noise. But what if you could mathematically model the noise and subtract it? You develop a system of conceptual coordinates. Every idea can be positioned in a multi-dimensional space based on its properties. The Greek logos might be at coordinates representing reason, word, and divine principle. Arabic concepts occupy their own positions. Translation becomes finding the Arabic concept closest to the Greek position in conceptual space. It's not perfect, but it's systematic and consistent. The translators are skeptical until you demonstrate with a test case. Take a Greek mathematical proof that's been translated to Arabic, then to Latin, then back to Greek. The final version is almost unrecognizable. But apply your mathematical correction system, accounting for the systematic distortions of each translation, and you can recover something very close to the original. It's like noise-cancelling headphones for ancient texts. The system evolves into something even more powerful. By mathematically mapping concepts across languages, you're creating a universal semantic framework. Scholars can express ideas numerically, independent of language. A mathematical proof written in your numerical notation can be understood by anyone who knows the system, regardless of their native tongue. You've invented a universal language based on mathematics, 1,000 years before Leibniz will propose the same idea. The secret society of translators decides you're either a genius or a sorcerer, possibly both. They adopt your system, and translation accuracy improves dramatically. But more importantly, the mathematical framework reveals connections between different cultural traditions that were hidden by language barriers. Indian logic, Greek philosophy, and Islamic theology turn out to have deep structural similarities when expressed mathematically. You're not just organizing knowledge anymore, you're unifying it. Back in Baghdad after your Spanish adventure, you find the city buzzing with a new challenge. The Caliph is planning the grandest construction project in the empire's history, a new palace complex that will dwarf anything built before. But there's a problem. The architects have designed something so ambitious that nobody knows if it's actually possible to build. They need someone to verify the mathematics before they start construction and potentially waste the entire imperial treasury. The plans are breathtaking. Domes that seem to float without support. Minaret spirals that twist into the sky like frozen tornadoes. Halls with acoustic properties that carry whispers from one end to the other, while maintaining privacy in between. Gardens with fountains that create geometric patterns with water. It's architecture as mathematics made manifest, and the mathematics is at the edge of what 9th century engineering can achieve. You start with structural analysis. The main dome is supposed to be larger than anything previously built, supported by a system of interlocking arches that distribute weight in ways that seem to defy gravity. The architects insist it will work. The engineers think it will collapse. You need to determine who's right using mathematical proof, not intuition. The calculations are staggering. Every brick, every beam, every decorative tile adds weight that must be accounted for. Forces flow through the structure in complex patterns. You develop what amounts to finite element analysis, breaking the structure into small sections and calculating forces for each. It's the kind of mathematics that modern computers struggle with, and you're doing it with pen and paper. Days turn into weeks as you work through the calculations. You discover that the architect's intuition is mostly correct, but with fatal flaws. The main dome will stand, but only if the supporting arches are precisely positioned, a deviation of more than 2 fingers width, and the whole structure becomes unstable. The spiral minarets are mathematically sound but will sway dangerously in strong winds unless internal counterweights are added at calculated positions. The acoustic halls present a different challenge. The architects want conversations at one end to be inaudible in the middle, but crystal clear at the other end. It's an acoustic focusing problem that requires understanding how sound waves reflect and interfere. You spend days in empty buildings clapping and listening, measuring distances and angles, developing mathematical models of sound propagation. The solution involves precisely calculated curves that look decorative but are actually acoustic lenses. The garden design might be the most ambitious element. The Caliph wants fountains that create patterns with water, geometric shapes that appear and disappear, telling mathematical stories through fluid dynamics. The architects have sketched beautiful designs, but nobody knows if water can actually be made to behave this way. You dive into fluid mechanics with an enthusiasm that concerns your colleagues. Water, it turns out, is mathematically fascinating. It follows rules, but those rules are non-linear. Small changes in pressure or flow rate create dramatic changes in behavior. You need to find the sweet spots where mathematics and water cooperate to create art. The breakthrough comes when you realize that water jets can be programmed like those textile looms you worked with. By controlling pressure with mechanical valves operated by water wheels, you can create sequences of jets that fire in patterns. It's a water computer, programmed with cams and gears, executing algorithms in fountain form. You design a fountain that displays the first 100 prime numbers in water. Jets fire in sequence, with the number of pulses representing each prime. Another fountain creates a water spiral that demonstrates the golden ratio. A third uses interference patterns between multiple jets to create standing waves that look like geometric flowers blooming and disappearing. It's mathematics as performance art. But the real innovation is the self-regulating water feature. Using principles similar to your irrigation management system, you design fountains that adjust their behavior based on water availability. During droughts, they automatically reduce flow while maintaining their patterns. During abundance, they create more elaborate displays. It's responsive architecture that adapts to environmental conditions through mechanical computation. The palace construction becomes a teaching moment for the entire empire. Young engineers come to study your calculations. Architects learn that beauty and mathematics aren't opposites but partners. Craftsmen discover that precision isn't just pedantry, but the difference between a standing building and a pile of expensive rubble. The construction site becomes an open-air university where mathematics is taught through practical application. 3 years into construction, disaster strikes. An earthquake hits Baghdad. Not devastating, but strong enough to damage the partially built palace. Several of the famous floating domes have cracks. One minaret lists dangerously. The Caliph is ready to execute the architects until you intervene with an observation. The damage follows mathematical patterns that reveal how to build better. You study the cracks like a detective studying clues. They're not random, they follow stress lines that your calculations predicted but underestimated. The earthquake has essentially performed a stress test on your mathematics, showing where theory meets reality and reality wins. It's devastating, but also invaluable data. The patterns reveal that your static calculations were correct, but you missed dynamic effects. Buildings don't just stand there, they vibrate, they sway, they breathe with temperature changes. The earthquake has shown you these movements in fast forward. You develop new mathematics for what you call living structures, buildings that move safely rather than standing rigid. The solution is counterintuitive. Instead of making buildings stronger, make them more flexible in calculated ways. Add joints that can move but only in specific directions. Use materials with different elasticities in mathematical ratios. Create structures that dissipate earthquake energy rather than resisting it. It's architectural aikido, using the earthquake's force against itself. You redesign the damaged sections with these principles. The new domes include hidden chains that allow controlled movement. The minarets get internal pendulums that counteract swaying. The foundations include calculated voids that absorb shock. It looks like the same design, but the mathematics underneath is completely different. The rebuilt palace is tested by another earthquake 2 years later, stronger than the first. This time the buildings dance but don't break. Witnesses describe seeing the domes ripple like water, the minarets sway like reeds, but everything returns to position undamaged. Your mathematical improvements have created architecture that's not just earthquake resistant, but earthquake adaptive. The Caliph is so impressed he orders all important buildings in the empire to be built or retrofitted using your methods. You've just invented earthquake engineering, saving countless lives over the coming centuries. Not bad for someone who started out just trying to make fountains dance. Drop a comment if you think mathematical architecture sounds cooler than modern skyscrapers, because honestly, making buildings that can dance through earthquakes is peak engineering flex. Your reputation has reached mythical proportions, which is why you're not entirely surprised when a mysterious visitor arrives at midnight, cloaked and clearly trying not to be recognized. It's the Caliph's chief advisor, and he has a problem that requires absolute discretion. The Imperial Mint has been producing coins with slightly less gold than claimed. Not enough for casual inspection to notice, but enough that someone with precise measurements has detected the fraud. The Caliph suspects corruption, but needs mathematical proof before he can act. The challenge is delicate. You can't openly investigate without alerting the conspirators. You need to develop a testing method that appears routine but can detect microscopic differences in gold content. The advisor gives you a single coin, the baseline supposedly pure standard, and tells you to figure out the rest. You turn to Archimedes' principle, but with a twist. Instead of just measuring displacement, you develop a system of comparative density analysis. By carefully measuring weight in air versus weight in water, you can calculate density to extraordinary precision. But that's not enough. You need to account for temperature variations, water purity, even air pressure. Every variable that could affect measurement must be mathematically modeled and corrected. The real innovation comes when you realize you can use statistics to detect fraud patterns. Random variations in coin weight are normal. No two coins are exactly identical. But deliberate fraud creates non-random patterns. Coins from the same batch will have similar deficiencies. The mathematical signature of accident is different from the signature of intent. You design what appears to be a quality control system for the mint. Officially, you're just ensuring consistency. Secretly, you're mapping the entire fraud network. Every coin tested gets logged with its weight, density, date of minting, and the shift that produced it. Patterns emerge. Certain shifts consistently produce lighter coins. The deficit follows a mathematical progression, starting small, growing bolder as no one notices. The mathematics reveals something unexpected. This isn't simple theft. The missing gold follows a precise formula, exactly enough to be profitable, but not enough to destabilize the currency. Someone with deep mathematical knowledge is managing this fraud. You're not dealing with common criminals, but with someone who understands monetary theory at a level that won't be common knowledge for centuries. Your investigation leads you deeper into medieval financial mathematics than you ever wanted to go. The fraudster isn't just stealing gold, they're using the stolen gold to manipulate markets. By calculating exactly how much gold they can remove without triggering inflation, they're essentially printing money. It's an economic attack disguised as simple theft. You develop a mathematical model of the entire economy. Money supply, trade volumes, commodity prices, everything gets equations. It's macroeconomics before anyone invented the term. Your model shows that the fraud, if continued, will cause a predictable economic crisis in about 18 months. Prices will spike, trade will collapse, and the empire's economy will implode. The fraudster isn't just a thief, they're an economic terrorist. But who has this level of mathematical sophistication? You cross-reference Mint employment records with the House of Wisdom's alumni. 3 names appear. All studied advanced mathematics. All now work in financial positions. One stands out, the deputy mint master, who wrote a treatise on numerical patterns in commodity prices 5 years ago. His mathematics is brilliant. His fraud nearly perfect. You need ironclad proof. The deputy is too smart to leave obvious evidence, so you set a mathematical trap. You propose a new coin design, with security features based on prime number relationships. The design is publicly about preventing counterfeiting, but you've embedded a hidden mathematical signature that will reveal any tampering. It's a cryptographic checksum, medieval style. The deputy, not knowing about the hidden signature, continues his fraud with the new coins. But now every fraudulent coin carries mathematical proof of its tampering. The altered weights destroy the prime number relationships in ways that point directly to the mint's production records. You've created a mathematical chain of evidence that even the caliph's judges can understand. The confrontation is anticlimactic. Presented with the mathematical evidence, the deputy confesses immediately. He knows the numbers don't lie. His plan was to accumulate enough wealth to fund a rival caliphate. He chose mathematical fraud because he thought no one would be sophisticated enough to detect it. He didn't count on you. The caliph is so disturbed by how close the plan came to succeeding that he establishes a new department, the Mathematical Guard, tasked with using mathematics to detect and prevent sophisticated crimes. You've just invented forensic accounting and mathematical criminology, medieval CSI, but with equations instead of DNA. The mint fraud investigation has unexpected consequences. The caliph, now paranoid about mathematical threats he doesn't understand, wants you to develop a comprehensive system for protecting the empire from what he calls warfare of the mind. He's realized that swords and armies are yesterday's weapons. Tomorrow's battles will be fought with numbers and ideas. You assemble a team of the best mathematical minds in Baghdad. Your mission sounds like something from a fever dream. Develop mathematical defenses against attacks that haven't been invented yet. It's the ultimate in abstract thinking. You need to imagine ways mathematics could be weaponized, then create countermeasures. The team starts with cryptography. Current encryption methods are basic, letter substitutions that any dedicated scholar can break. You develop something revolutionary, encryption keys based on mathematical functions. The sender and receiver agree on a function. Messages are transformed using this function. Without knowing the function, decryption requires solving mathematical problems that would take lifetimes. It's computational security before computers exist. But encryption is just the beginning. You realize that information itself can be a weapon. False mathematical models could lead to bad decisions. Corrupted calculations could cause bridges to collapse, irrigation systems to fail, navigation to go astray. You develop verification methods, mathematical checksums that can detect if calculations have been tampered with. It's data integrity for the pre-digital age. The team makes a disturbing discovery. By analyzing trade records with your statistical methods, you can predict political instability, certain patterns in commodity prices, migration flows and tax revenues precede rebellions with mathematical regularity. You've accidentally invented predictive analytics for social unrest. The caliph is thrilled. His enemies are terrified. The ethical implications keep you awake at night. Mathematics as a tool for predicting and preventing rebellion could maintain peace or enable tyranny. You build safeguards into the system, mathematical limits on surveillance, statistical thresholds that prevent false positives from triggering oppression. You're trying to create ethical algorithms in an age when most people don't even know what algorithms are. The year-long project culminates in a sealed document, the Mathematical Defense of the Realm. It contains encryption methods that won't be rediscovered until World War II, statistical techniques that preview modern data science, and ethical frameworks for mathematical governance that modern tech companies could learn from. The Caliph locks it in his most secure vault, to be opened only in dire emergency. The knowledge is too dangerous for regular use. You've just written the medieval equivalent of nuclear weapon designs, except your weapons are made of pure mathematics. 10 years have passed since you first arrived at the House of Wisdom with a headache and a talent for mathematics. You're older now, perhaps wiser. Certainly more cautious about the power of numbers. Today you're facing your greatest challenge yet, not a practical problem from the Caliph or merchants, but a philosophical question that threatens to unravel everything you believe about mathematics itself. It started innocently enough. A young student, barely 16, approached you with what seemed like a simple question. If mathematics is universal truth, why do different mathematical systems give different answers? She's discovered that Indian mathematicians, Greek geometers, and Arab algebraists sometimes reach contradictory conclusions, not because of errors, but because they start from different assumptions, which mathematics is true. You try to dismiss it as a beginner's confusion, but she persists with examples that make your head spin. In Euclidean geometry, parallel lines never meet, but navigators using spherical geometry know that great circles, which are straights on a sphere, always intersect. Indian mathematicians accept infinite quantities. Greek mathematicians reject them as logical impossibilities. Both create internally consistent systems. Both work in practice. How can contradictory things both be true? The question spreads through the House of Wisdom like wildfire. Scholars who haven't spoken in years are suddenly debating in the corridors. The very foundations of mathematical certainty are shaking. If mathematics isn't universal truth, what is it? A human construction, a useful fiction, the tool you've used to revolutionize everything from irrigation to cryptography, might be built on sand. You spend sleepless nights grappling with the paradox. The answer, when it comes, is both disturbing and liberating. Mathematics isn't one truth, but many truths. Each mathematical system is like a game with rules. As long as you follow the rules consistently, you get valid results within that system. The question isn't which system is true, but which is useful for your purpose. Euclidean geometry works for buildings. Spherical geometry works for navigation. Both are true within their domains. This realization transforms how you teach mathematics. Instead of presenting theorems as divine truth, you present them as choices. Start with these assumptions, follow these rules, reach these conclusions. Different assumptions lead to different mathematics. It's intellectual freedom that would terrify religious authorities if they understood the implications. You're essentially saying that truth itself is relative to your starting points. The philosophical crisis deepens when another scholar raises an even more troubling question. If mathematics is just a system of rules we choose, why does it work so well at describing reality? Why do planetary orbits follow ellipses? Why do population growths match exponential curves? Why does the universe seem to speak mathematics? You organize a grand symposium to address these questions. Scholars from every tradition gather. Platonists who believe mathematics exists in an ideal realm. Formalists who see it as symbol manipulation. Intuitionists who trust only what can be constructed. The debates are fierce, sometimes literally. One argument about the nature of infinity ends with thrown manuscripts and broken inkwells. But from the chaos emerges a beautiful idea. Perhaps mathematics works because we've unconsciously selected the mathematics that works. Over centuries, humans have developed mathematical tools that match reality because non-matching tools were abandoned. It's intellectual evolution, survival of the fittest equations. The universe doesn't speak mathematics. We've learned to speak universe. This leads to a revolutionary research program. Instead of assuming mathematics describes reality, test which mathematics best describes which aspects of reality. You organize teams to systematically try different mathematical approaches on the same problems. Treat mathematics as hypotheses to be tested, not truths to be accepted. The results are stunning. Problems that seemed impossible with one mathematical approach become trivial with another. Astronomical calculations that required pages of geometry simplify to lines of algebra. Economic models that failed with linear equations succeed with recursive functions. You're not discovering mathematical truth, you're discovering mathematical fitness. Different mathematics for different purposes. The implications ripple beyond the house of wisdom. Craftsmen start experimenting with different geometric systems for different materials. Merchants develop specialized mathematics for different trade routes. Architects create building-specific mathematical languages. The rigid unity of mathematics explodes into beautiful diversity. It's mathematical biodiversity, each species of mathematics adapted to its ecological niche. As your career in the House of Wisdom draws to a close, you're asked to give a final lecture, your mathematical legacy for future generations. The hall is packed. Students, scholars, craftsmen, even the Caliph himself have come to hear your final words on the nature of mathematics and its role in human civilization. You begin with a confession. When you started, you believed mathematics was the language of God, eternal and unchanging. Now you know it's the language of humans, evolving and adapting. This isn't a loss of faith, but a gain of wonder, that human minds can create tools that unlock the universe's secrets is more miraculous than finding those tools ready-made. You trace the journey from those first hungover mornings, solving inheritance problems to redesigning cities, from translating ancient texts to preventing economic warfare. Each problem required not just applying mathematics, but inventing new mathematics. The Islamic Golden Age isn't just preserving Greek knowledge, it's exploding beyond it in directions the Greeks never imagined. But your most important point is about the democratization of mathematics. The Greeks treated geometry as philosophy for the elite. Indians developed arithmetic for astronomers and priests. But here in Baghdad, mathematics has escaped the ivory tower. Weavers use it to create patterns. Merchants use it to manage risk. Farmers use it to optimize irrigation. Mathematics has become a tool for everyone, not just scholars. You warn against the dangers too. Mathematics can be used to oppress as easily as liberate. Statistical models can justify prejudice if fed biased data. Encryption can hide truth as well as protect it. Optimization can create efficiency at the cost of humanity. The same mathematics that predicts eclipses can predict and potentially control human behavior. With great mathematical power comes great ethical responsibility. Your final revelation is personal. The real magic of mathematics isn't in the numbers themselves, but in how they change the way you see the world. Once you understand mathematical patterns, you see them everywhere in the spiral of a shell, the branching of rivers, the rise and fall of dynasties. Mathematics doesn't just solve problems, it reveals the hidden connections between all things. The universe isn't just described by mathematics, it's poetry written in equations, waiting for those who learn the language to read it. As you conclude, you issue a challenge to the assembled crowd. Don't just learn the mathematics we've developed. Create new mathematics. Find patterns we've missed. Solve problems we can't even imagine. The Islamic Golden Age isn't ending, it's just beginning. Every person who picks up a calculating board or astrolabe carries the revolution forward. The audience erupts in applause that echoes through the marble halls. Students rush forward with questions. Scholars debate your points. Craftsmen sketch new applications. You've lit a fire that will burn for centuries, through the translation movements that bring Islamic mathematics to Europe, through the Renaissance and scientific revolution, into the modern age where algorithms shape reality, and mathematics has become so powerful, we've had to invent ethics committees to control it. As you walk home through Baghdad's dusty streets, one last time, past the merchants using your randomized shipping routes, under the arches built with your earthquake-resistant architecture, listening to the fountains playing mathematical melodies, you realize something profound. You haven't just witnessed the Islamic Golden Age, you've helped create it, one equation at a time. The muezzin's call to prayer echoes across the city as the sun sets, painting the sky in shades of gold and crimson. You pause, appreciating the mathematical precision in the call's timing, calculated to the minute based on astronomical observations. In a world where many are still navigating by superstition and tradition, you've helped build a civilization that navigates by knowledge and reason. Not bad for someone who started with a headache and a confusion about Arabic numerals. Let me know in the comments what mathematical innovation from the Islamic Golden Age surprised you most. Was it the earthquake-resistant architecture, the economic fraud detection, the universal library classification, or maybe the idea that mathematics itself is more diverse and flexible than we often assume? Like and subscribe if you want more deep dives into historical periods that were way more advanced than your high school history teacher let on. And remember, next time you use the number 0, calculate with algebra, or navigate by the stars, you're using tools perfected in the halls and markets of medieval Baghdad, where mathematics wasn't just academic exercise, but the beating heart of a civilization reaching for the stars, with nothing but human ingenuity and the power of the mind.